So we're doing fractal landscapes, which are procedurally generated landscapes that also have like a random component so that they can be like changed and look like organic real landscapes, which we started out by doing in MATLAB and seeing. This is actually from our FPGA code. It's a little easier to visualize here in 3D. These landscapes that are generated that look like totally real landscapes. And we figured this would be a good application for the FPGA because it can be very parallelized and doing all these steps of calculating these different points in parallel. It's something called the diamond squares algorithm that we use to calculate this, where you start with just a few points in a diamond pattern, and then move on to a square pattern, and then kind of do that fractally until you cover every point in the matrix. Which are some diagrams of that in our.
By fractal, you mean subdividing?
Yeah.
Yeah.
And I see that this particular example has kind of a ridge down the middle.
Mm-hmm.
Is that totally random, or did you bias it slightly?
No, yeah. The only thing that we set out is the 4 corner points and a random seed. So what we're doing by changing this index is giving it the random seed, which will change it to be just the value of the random LFSR that comes out.
Cool.
Yeah. So we just had that which is why the HPS, and so one of these is this is the FPGA and this is the HPS, and that's why they're different. Is because the HPS is generating different random values, even though it's doing the same algorithm, just by the way the random algorithm works on that system.
The way that the random one works too is that like I've seeded it using the same seed that's written so that it can like for example, if I seeded it with like the current time, then it wouldn't ever be the same if we like type the same seed. So if you wanted to like go back and like see what it was at like seed 5, then it'll go back to like what it was. And so like in that sense, it's the same randomness, I guess, as the HPS or as the FPGA, because with a random seed, the FPGA will also generate the same thing because the LFSRs are not totally random either.
Well, which is good. It's a feature, I would say. It's not a bug.
Yeah.
Yeah. Oh yeah, definitely.
Yeah. But yeah, like so. Kind of to expand on like the diamond square algorithm that Katie was discussing, there's like a really good diagram of it on Wikipedia, which is actually, do you want to pull up bigger stuff, Katie?
Yeah, I'll pull up bigger stuff.
Oh yeah.
Okay, I'm not sure what's gonna be on my screen when I open this up, but we'll see. Okay, I'll just do this.
But yeah, so like kind of what helped us like visualize like how the actual algorithm works is by like drawing it out in an Excel sheet. And so essentially you can see that like the pattern of what points are being pulled to average changes in every other step. And each of those consecutive steps counts as one iteration. And so the number of iterations that happen, we can call as n. And so then the side length from that is 2 raised to the n minus 1 or plus 1. And so we had some like, so originally our goal was to like make this 512 by 512 to like max out our M10K possibilities. But then as we were putting stuff on hardware, we noticed that like the design was not scaling linearly. And so it was like we weren't M10K limited. And so we weren't able to like get a full 512 by 512 image. And also the max possible like size that we could have done would have been 513 by 513 because of the way that the fractal landscape like side lengths work. So like if you do n equals 9, then you would get a 513 by 513 square. And so we would have had to have like an extra row of registers anyway. And so we decided to focus on like trying to get anything to compile because the size was just like messed up. And so part of the problem was that like, it's like we were saying, right? Like the size of the computation changes as you're going on. And so you need to have like all of this hardware generated beforehand so that it's available like at the time that you need it.
Yeah.
So what side length were you able to get?
N equals 6, so 65 by 65. Then we wrote each pixel like 4 times in the little box, so it should be bigger, you can see it better.
Okay.
Yeah, and for any of these given steps, like all of the points in yellow are the ones to be calculated, and you start getting more and more of them very quickly. And in principle, all of those can be calculated in parallel because in a given step, you're calculating all the yellow points, and the data that you need to calculate those is the green points, which were already calculated previously. So in principle, you could calculate them all in parallel, which would maybe work well, like right at the beginning, or if you were working with a very like small grid. But I like even for a relatively like small one like this, which is only 17 by 17, you quickly run into like towards the end, you need to calculate a lot of points simultaneously. So rather than parallelizing every single point, we opted for sort of a scheme similar to the drum, where we have a column parallel row serial type approach, where it's a little bit more complicated because the algorithm is broken up into diamond steps and square steps, where in a diamond step, you're sort of calculating these yellow points, which you can see are organized nicely into columns. But in the square step here, you can see that they're not in columns. So you kind of need to switch around how you're doing, but you can still sort of parallelize across like 4 or 5 columns in this case. And so our parallelization ideally was supposed to scale linearly with the side length as opposed to square with the side length if we were to parallelize every point. But there was some part of our logic that started to blow up very quickly in terms of ALM utilization as we increased the size.
You can see what kind of these purple points are the points being calculated in each step. And so you can see it switches between like, you know, these middle ones and these outer ones, these middle ones. And so it switches around of what points you're exactly like looking at.
Yeah, and kind of like the fix, like Alex was mentioning too, about like the fact that we were running out of ALMs was, we had a discussion in lab where we noticed that like a lot of our logic was nested. So we had these like huge case statements that was like, okay, so for the diamond step, depending on our iteration number, we would change the amount we were shifting by because the for loop's size would change. And you can't have like a variable number being iterated in a for loop because Verilog doesn't like that.
Well, if you're building hardware, you can't build variable hardware and then use it, right?
Yeah, exactly. Like it's not like compile time defined. And so how we fixed that was we made a state machine that like is currently 50 states. And it essentially just like unfurls the thing. So it's like a single stripe that only like the condition is only on we call like a new state variable. And that just like keeps iterating. And so it made the ALM usage a lot smaller, but we still wouldn't be able to fit like another n = 7.
So can I paraphrase this? I want to see if I understand what you're saying. So there's the way you organize the program then is that the design is that there is a separate solver for each different resolution. Mm-hmm. You step between solvers. Mm-hmm. Is that true? Yeah.
Yeah.
So instead of going as order n in number of it goes to something like n log n or something. So or n to the 3/2 or some.
Because there's still only like one diamond step and one square step for each of the iteration numbers. Yeah. But the reason it's broken up into 50 is because there's like one for setup, there's one for like for each step, there's one for like doing the odd steps of the diamond of the square step and one for doing the even steps. So it's not like there's like one for each like literal column or anything like that. It's just
Cool.
Yeah. So
yeah, when you were updating that screen, those were real-time updates?
Yeah, this is just like you can type in whatever seed you want, and it will give you a real update. This one is the FPGA and some of the HPS, and you can actually see how much faster the FPGA is. Like it updates first.
It updates first.
Wow.
Yeah, it's like, I think I did the math, and it's like over 4,000 times faster.
What?
You can see the FPGA time and the HPS time. So the thing is, the FPGA, we're not accounting for the time it takes to write to the screen. We're just accounting for the time it takes to like calculate all the points because passing over the points is a little bit like not really part of our algorithm and just kind of slow. But
Yeah, the HPS time also doesn't include the the VGA time either.
Yeah.
Wow.
Like, it writes the VGA after recalculating.
That's impressively
That's
fast.
awesome. That's awesome.
Very parallel.
That's a great statistic to have.
Sorry, I was just gonna say it was kind of funny, like running this in Model Sim, because we had sort of like a fake VGA state machine, so we could see like on the time axis, like the amount of time spent actually solving the algorithm, and then the amount of time spent writing to the VGA. And it was like when you were zoomed out enough that you could actually see the VGA writing, like you couldn't even see the algorithm solving anymore. It was just like a line at the very beginning.
I believe that.
Yeah, and like that's kind of why we chose not to write the VGA screen at the same time that we were solving, because like that would, yeah, like that it wouldn't have gained us that much.
Yeah.
So now you can use the power estimator. I think even without recompiling or anything, you can use the power estimator to get the power estimate of separately of the FPGA and the HPS, multiplied by the time, and you have the energy difference between the two. And I'll bet that the energy difference is fantastic.
We'll take a look.
Yeah, take a look. I mean, that's worthwhile. That's a fast thing to do, and it's a nice statistic. Because since the power of the FPGA is usually around half or a third of the HPS, and you're only taking 1/100th of the time or something ridiculous, or 1/1000th of the time.
1/4000th.
1/4000th. The energy use is going to be minuscule compared to the HPS.
I guess one thing that we forgot to mention is like how we generated this MATLAB thing is like not a one-off thing. Like we were able to like pipeline all the values to the HPS like into a file so that we can like visualize it in 3D, since we didn't get to that part of, I mean, that was never our original intent, but like we didn't add that feature, I guess, to our VGA setup.
Sure. Yes, we have a script that will write it to a file on the HPS. We SCP it over to, oh my God, what? My caps lock is on. We SCP it over to the lab computer, and then we can run the script in MATLAB that just takes that file and makes a mesh out of it, and you can see it in 3D, which is pretty cool. So this is the same thing that's on the screen right now.
Have you tried surf rather than mesh?
You can't. So this yeah, we had that on our computers, but this like MATLAB 2016 or whatever like doesn't vibe with that. So
that's
and the camera crashed. But yeah, we did that, but it didn't work. But mesh is cool too. So
yeah, it's because like I think that the heights do correspond slightly to like the colors, but it's not as like straightforward as you would think, because now the other thing that we did was we originally had 10-bit calculations, and then we scaled everything down to 8-bit to fit it.
And it would be better to have 8-bit too, because with 8-bit you can just directly pipe the value to the pixel color, and so it's like a direct mapping as opposed to like having 10 values where we show kind of like a low quality map.
It does make it a little bit harder to interpret like what's actually happening from the images on the VGA, but you still get kind of an idea of like the contour.
They still look organic. They still look.
Yeah.
Oh, you're saying it because of the RGB encoding, the colors on the screen are not monotonic with altitude.
Yeah, exactly.
They're not. They don't follow a path in hue space.
Yeah, I'm actually pretty sure this is like the opposite. Like if you look at like where these blues are, it matches where the reds are on this screen. So I'm pretty sure it's actually like flipped.
Interesting.
You know what I mean? I think these are the dips.
I wonder how monotonic colors in nature are with altitude. Like I wonder what the most organic looking color map actually is.
I think it's a rainbow, because that's a natural phenomenon. It's like that's what the spectrum of light is, right? Or maybe grayscale. I don't know.
Well, but if you take into account the surface reflectivity, then
of course,
mountains are at the very peak are often white.
Oh, I guess something very important that I kind of forgot to mention is how this algorithm actually works. Is it takes the average of the points around it and it adds a random value, which is why you see patterns and not just complete chaos.
Yeah.
So like the very first step, it'll just take the 4 corners that we input and average them and add like a random component. And then every time we go to a new iteration, so this is a diamond step and a square step, and then we go to iteration 2, diamond step, square step. Every time we do that, we shift the random number by a bigger value so that it's not like totally, again, it's not total chaos. Like you have like lower and lower deviation from the average, so it looks pretty natural. Yeah.
That's really nice.
Next.
I wish there was a way to like screen capture the VGA screen. Like,
ooh, would that be nice? That sounds like
just because the colors here are like, I know, not as vibrant.
Yeah, I actually got into lab last night because Parker was there, and I took some photos, which are pretty cool. And they look a lot better than this does.
So
not in our report.
So you could, let's see, if you slurp that giant memory across to the HPS, I said, oh yeah, that's quite different, isn't it?
This is what we see, Hunter, when you go in and look at our.
Yeah, if I happened to be remoted in, and I was like futzing with the code a bit, and then I saw Katie, and I just saw her phone, and I was like, Katie, are you in lab? And she was like, yeah, I'm in lab. And I was like, let me take a picture of you.
Nice.
Yeah.
Especially, I mean, you could slurp that image directly across, right, as an image.
Yeah, I mean, this is what the MATLAB is just pulling like the points from the points of the VGA SRAM. Because we use that VGA to write to SRAM.
In MATLAB, you can control the color of every vertex in MATLAB if you care to.
Yeah.
And therefore, you could make that the same color map as the VGA.
Yeah.
Yeah,
that would work.
Yeah.
That would be sick.
That's basically what we did, except for like we just chose a different color scheme and like made it 3D.
Yeah.
So, yeah.
Cool.